Hello everybody, welcome to my presentation. My name is Farouk Aichouche. I am PhD student in Montpellier University. So I will talk about my paper published in ECC 20. The title is Flexibility of Waste Resource Recovery Facilities for Water Reuse. So in the outline of my talk, I'm going to start by talking about the motivation that led us to state the flexibility of wastewater treatment system and define our goals. Then I'm going to move on to plant description that we will describe a flexible platform and illustrate the various compartment used. After that, we define the processes model used and how we analyzed the structure by manipulating the different sub-configuration, and we will finish with the results and their discussion, and finally by conclusion. We start with the motivation. In most regions of the world, more than 70% of tap water is used for irrigation. And according to change of paradigm from wastewater treatment plants to water resource recovery facilities, so the traditional wastewater treatment plants are increasingly regarded as water resource recovery facilities because of reflecting the value of water, nutrients, and other resources, in addition ensuring the required effluent quality. But resource recovery units will need an improvement performance to be operated in a relatively stable condition and not with the same dynamic as in wastewater treatment plants. The objective is to do things differently. Instead of just doing the traditional wastewater treatment and eliminating pollution to respect standard imposed, why not think of a more flexible system that allow traditional treatment during one period and the recovery resource in another period? The idea is to close the loop between the flexible wastewater treatment plant and the plant needs, which are provided by the sensor or observer of plant. The approach is to reuse treated wastewater for irrigation during period of water stress. In other words, conserve some nutrients in treated wastewater for plant needs, or to do full treatment outside irrigation period. This operation requires a transition between two operation modes, reuse mode and full mode. Now we present the platform proposed. So the flexible platform configuration consists of one anoxic tank number 4 in figure, followed by aerobic tank number 5 in figure, and aerobic tank with membrane number 6 in the figure. The membrane is supposed to be ideal, the perfect separation of soluble and particulate matter. In other words, the following phenomena is not taken in account. The platform can be operating by step feed as one stage only tank number 6, or two stage with tank 5 and 6, or with three stage with tank 4, 5, and 6 by adjusting effluent feeding location, Q in, and the recirculation rate. The denitrification takes place in anoxic tank number 4, while the nitrification and carbon oxidation are accomplished in both aerobic tank number 5 and 6, and also three valves, A, B, and C, are assumed to have two positions. One external recirculation QX depends to position of valve C. We can redirect it aerobic tank number 5 when C position equal to 1, or to anoxic tank number 4 when the valve C position equal to 0. And another internal recirculation from aerobic tank number 5 to anoxic tank number 4. Also, the dissolved oxygen in both aerobic tank is maintained at 2 milligrams per liter. Now we present process model. So the biological reaction inside each reactor in the platform are modeling using ISM1 2ND model. Is a modified model of ISM1. The main modification consists in the addition of two-stage processes for nitrification and denitrification. While in the ISM1 model, figure in the left, consider only complete nitrification of ammonia in H4 to nitrate NO3 by autotrophic bacteria XBA, followed by complete denitrification of nitrates to nitrogen gas N2 by heterotrophic bacteria XBH. ISM1 2ND use a two-step for nitrification. The first one describing the ammonium and H4 oxidation to nitrate NO2 by ammonium oxidizing bacteria XAOB, while the second step the nitrate NO2 oxidation to nitrate NO3 by nitrate oxidizing bacteria XNOB. The denitrification is performed following a parallel two-step in which nitrate or nitrate are transformed into nitrogen gas N2 by heterotrophic bacteria XBH. This model was chosen because we can quantify all forms of nitrogen. So for structure analysis, in order to analyze the WRRF platform, we start by defining the property of each desired operating mode, reuse and full mode, and the next step consists in determining the operating condition and find candidate controlled variables. After that, we propose various scenarios to testing and determining the best transition strategy in terms of response time. To remember what we mean by response time of transition is the time required to move from one mode to another. So now we define operating mode property. In the reuse mode, it's necessary to find a condition in which the biological treatment will make it possible to preserve the nitrogen and therefore NH4. So the nitrification will have be limiting. It means that the sludge age SRT must not be too high. This mode will be used in period of stress for recycling of water and nutrient as an H4 and reducing freshwater withdrawal. For second fuel mode, must make nitrification and denitrification possible. So the sludge age SRT must be sufficient. This mode should be used outside irrigation period to limit pollution of water reserve. Now we define the operational condition. The sludge retention time is one important parameter for design and control in activated sludge processes. It represents the average length of time that bacteria stay in a reactor before being wasted. The selected SRT directly affects the processes in an activated sludge system. This parameter contains a critical value called SRTM, or the minimum SRT in literature is defined as the opposite of growth rates minus mortality of nitrifying biomass. So to choose SRT higher than this value, the system can operate without loss of nitrifying biomass. As you can see in figure on bottom, for limiting nitrification, it is necessary to choose an SRT lower than SRTM. Will you choose an SRT higher than SRTM, the nitrification can take place. Now, position valve analysis. So in order to analyze the platform and determine the best transition strategy in terms of quality and response time, it's necessary to identify the scenario for each mode of operation. Each scenario represents a combination of valve position. We study switch of environmental condition, position of valve, and value of control signal. Different switches are simulated from one scenario to another, and corresponding response time are observed. It means the time required for the system to switch from one steady state to another one. In each mode or scenario, we selected the value of sludge age, or WRS, and the value of recirculation rate. It should be noted that the valve in different configurations are supposed to be all or nothing. Each value represents a direction of corresponding flux. The first two scenarios are used to reuse mode, while the second two scenarios represent the full treatment mode. Now, to study the influence of the switch time on the response time, we tested this transition from scenario S1 reuse. As we can see in the figure at the left, their corresponding configuration to the scenario S3 or the full mode, figure on the right. Two transition moments, the first at 200 days and second in 100 days. It's important to remember we have different initial conditions at time of switch. So the figure shows the transition from scenario S1 reuse mode to scenario S3 full mode at 2 time transition 100 days and 200 days. Different initial condition at the time of switch explain the observed difference response time. Remember that the nitrifying bacteria growth exponential. At 200 days dashed line, the first transition occur at this instance, the biomass concentration is lower than when the transition occur at 100 days. In other words, the more the bacteria are subjected to a higher waste sludge flow for prolonged time, the more their concentration are diminished. Now we want to say influence of returned sludge direction. The figure on the bottom shows the comparison between two transition cases. The first one is the switch from scenario S1 to S3, while the second transition from scenario S1 to S4. The main difference is in the direction of external recirculation. The first continuous line is slower to the second one. So when the returned sludge was directed to the aerobic tank at the instance of transition, promote the growth of nitrifying bacteria since it reduced the lake phase. The third transition is done to say the effect of deletion on returned sludge. The transition is done at 200 from the scenario S1 to S4 in considering two different values of returned sludge that were 100 liters per day and 270 liters per day. When the returned sludge equal to 100 liters per day, dashed line, the time response was shorter than 270 liters per day in continuous line. Since low returned sludge flow mean low deletion rates and more concentrated biomass and nutrients. So all the transitions that have been tested before, they have a very important response time, even if we have a better one to another. So the next strategy, it focuses on use of bioaugmentation or addition of nitrifying bacteria to minimize the time to switch from S1 to S4. For the simulation viewpoint, it's equivalent to change the initial condition of nitrifying bacteria, its AOB and its NOB in a reactor at moment of transition. In figure, both profile are represented when the added of 10 milligram per liter in dashed line and when the added of 1 milligram per liter in continuous line. Both strategies have less response time than all of previous strategy, but with the addition of 10 milligram per liter, it means addition more nitrifying bacteria is a little faster than the addition of 1 milligram per liter. Also, we can say when we added 1 milligram per liter, a partial nitrification was observed because of insufficient concentration added. Now, two transition cycle from reuse to full mode are simulated. The first cycle was performed after 100 days of operation in reuse mode to full mode, and the switch after that to the reuse mode and stay 200 days for switch again to full treatment mode. In the conclusion, the new platform allows users to take advantage of more degree of freedom than classic configuration. The basic objective is to improve the transition operation between the resource recovery mode and the conventional treatment mode. Various possible scenarios minimizing the time needed to switch from one mode to another, and the response time for a transition from the reuse to full mode depend on the time during which the complete mode is set. Because of different initial states, an improvement on the response time is obtained while the bioaugmentation strategy is applied. And finally, it will be interesting to investigate extension of the result to take into account dynamic effluent flow. And thank you for your attention.